We covered this earlier in this module, but here's the incremental risk equation one more time. We're going to start with the calculation for the annual probability of failure, or APF, which is the product of the hazard probability and the system response. Please take a moment to download the companion spreadsheet from the website to help you follow along. It is recommended that you use these worksheets to work through the example calculations as they are demonstrated. Here are the steps for calculating the annual probability of failure. To calculate the marginal annual probability of failure of a potential failure mode, we'll start by discretizing the hazard into intervals. We will calculate the probability of each hazard interval and then multiply the system response at the midpoint of each hazard interval by its corresponding hazard interval probability. Lastly, we'll sum the result for all the hazard intervals, which will give us the annual probability of failure. When we calculate the total risk, as we discussed in Module 1, we need to combine the PFM risk estimates in a way that is technically correct so that we do not artificially inflate the risk. So to calculate the contribution of each PFM to the total risk, we will follow the same procedure as for calculating the marginal APF, but we will select a risk model, such as competing risk, to adjust the system response probabilities. And we will then use those adjusted system response probabilities instead of the marginal system response probabilities in the calculation. The first step is to discretize the hazard into intervals. Discretizing is just a fancy word for splitting or partitioning. When we split up the hazard into intervals, we want these intervals to encompass the full range of the hazard. These hazard intervals do not need to be even, but that is typically where we start. When the system response probabilities or consequences are sensitive to small changes in the hazard, smaller intervals around those critical loads will provide better precision and yield more accurate results. Your other option would be to increase the overall number of partitions, which will lead to smaller intervals and better resolution. Because we are working with annual exceedance probabilities, the probability that a given hazard will be met or exceeded each year, the probability of being within a given hazard interval is going to be equal to the difference in the exceedance probabilities of the hazards that define the interval. We should include both non-exceedance and exceedance within our intervals. In a stage frequency curve, the first peak stage of the curve will have an exceedance probability that is close to 1, but less than 1. From Module 1 of the course, we learned that the sum of the probabilities originating from a single chance node must be collectively exhaustive and summed to 1. To satisfy this rule, we need to add in the small probability of having a peak stage less than the first stage of the curve. This is the non-exceedance probability. In the plot on the screen, the first stage of the curve has an annual exceedance probability of 0.99, which means there's a 99% chance that the stage will be exceeded each year. It also means there's a 1% chance that it will not be exceeded. To account for this 1% and to make everything sum up to 1 and satisfy our event tree rules, we're going to add this non-exceedance probability to the probability we calculate for our first stage interval. A couple things on partitioning. The partitions do not have to match the hazard values that are given. In this example, the black points here define the stage frequency curve, but we can pick our intervals between those points and simply interpolate to get the annual exceedance probability for the stage that we have selected to define the interval. Also, to reiterate what I've covered on the previous slide, because the probabilities given for each stage are exceedance probabilities, we need to subtract the probabilities of the stages that define the interval to calculate the probability of having a peak stage that falls within that interval. In the example, stage 1 is exceeded 99% of the time. In stage 2, it's exceeded 90% of the time. Therefore, the probability that a peak stage falls between stage 1 and stage 2 is equal to 9% each year, or 99% minus 90%. The table on this slide illustrates the discretization process and how to calculate the probability for each partition or interval. The table shows how to account for non-exceedance and exceedance probabilities. The non-exceedance probability, as we just discussed, is added to the probability of the first interval. The exceedance probability is accounted for in the last interval and is simply the probability of exceeding the last hazard used to define the hazard curve. The hazard may be bounded by a state variable like stage, but unbounded by probability. For example, if we bound the stage frequency curve at the probable maximum flood, the stage frequency curve would go horizontal upon reaching the probable maximum flood and stay that way forever because the zero cannot be plotted on a probability scale. Essentially, we would be limiting the hazard range that we are considering so that the last interval, interval n, would be removed from the calculations because we are saying that we cannot exceed that stage. The formulas for discretizing into even intervals are provided at the bottom of the slide. The default for tools like RMC QRA Calcs and RMC Total Risk is to use even intervals. But like I said earlier in this presentation, if you're going to use even intervals, you need to make sure you use enough of them to account for inflection points in the hazard curve, the system response, and the consequences. Also, when we say even intervals, we mean all but one even interval because the last interval will be for the exceedance probability. So for n equals 10, we will end up with 10 total intervals, 9 that are evenly spaced, and then one interval for the exceedance. Here's where you will want to start using the Module 2 example spreadsheet that I mentioned earlier to help you follow along. We were given a stage frequency curve with the data shown in the table on the left. On the plot to the right, the black diamonds correspond to the stage annual exceedance probability, or AEP points, that are shown in the table. We are going to discretize into even intervals. The red triangles are the stages that split the curve into 10 even partitions. For a given interval, the probability of reaching a peak stage within that interval is equal to the annual exceedance probability of the interval's lowest stage minus the annual exceedance probability of the interval's highest stage. So for the second interval between peak stages A1 and A2, the probability of that interval will be equal to the annual exceedance probability of A1 minus the annual exceedance probability of A2. You can see here that the non-exceedance probability, 1 minus the annual exceedance probability of the first stage, is at the bottom of the plot. This should be added to the first interval. Here are the interpolated annual exceedance probabilities for the stages that define our partitions. The probability for each interval is calculated by taking the annual exceedance probability at the lower stage minus the annual exceedance probability of the highest stage. The probabilities are the same ones shown in red on the prior slide that we interpolated from the stage frequency curve. The non-exceedance is added into the first partition, and if everything is done correctly, all these probabilities will sum to 1. When we are calculating risk, we are essentially calculating the area under a consequence frequency curve that is derived from the hazard, the system response probabilities, and the consequences using the trapezoidal rule. The discretization or partitioning gives us the trapezoids. This is also essentially what we are doing with the event tree calculations. We develop a branch for each hazard partition, assign the system response probability and life loss that best represents the interval, and then the frequency or the y value of the trapezoid will be the product of the hazard probability times the system response, and the x value will be the change in the consequences. We can then multiply x and y for each trapezoid to get each area and then sum them up to get a good approximation of the area under the curve. With regards to the number of intervals that we need, it's good practice to use at least 50 intervals, but this is arbitrary. The key is to have enough intervals, evenly spaced or not, to adequately account for the inflection points in the input curves. We'll move into potential failure modes and their associated system response probabilities. We will step through the calculations for PFM1, concentrated leak erosion along the conduit. The calculations for the backward erosion piping failure modes, PFM2A and PFM2B, are included in the companion spreadsheet, but will not be covered in detail in the presentation, because the calculation procedure is the same as that for PFM1. So, with the stage frequency curve discretized and probabilities calculated for each interval, the next step is to calculate the system response probabilities for each interval. When we develop our system response curve, we need to evaluate enough stages to cover the full range of the hazard. Possible inflection points can be related to performance observations, changes in geometry or geology, and hydraulic conditions, like top of active storage, above which tailwater may increase. Also, it's always good to define your system response probabilities at least up to top of dam, not just the probable maximum flood, because as data and methodology change and improve, that probable maximum flood elevation might also change. The system response probabilities, at least for this failure mode, are estimated as a function of peak stage. For calculating the annual probability of failure, we will need the system response probabilities at the midpoint of each of the hazard intervals that we created earlier. For each interval, we're going to take the midpoint, which is the average stage for that interval, and then we're going to interpolate from the system response curve to get the probabilities. Here, a logarithmic transformation was used when interpolating to get the system response probabilities. Z-variate would have been marginally better at linearization, but not enough to make a meaningful difference. So let's use logarithmic interpolation because it's much easier to plot in Microsoft Excel. Just to reiterate, we take the midpoint stage of each hazard interval and interpolate to find the system response probability for that midpoint stage. Now that we have hazard probabilities and system response probabilities for each hazard interval, we can calculate the annual probability of failure. This is done by multiplying the hazard probability by the system response probability in each hazard interval, then summing those products together. In this example, the annual probability of failure turns out to be 5.07 times 10 to the minus 4. Calculating the annual probability of failure was the first part, but it's not risk until we consider consequences. Next, we will calculate the average annual life loss and the average incremental life loss. To do this, we start with the calculation for incremental life loss, and like the system response probabilities, we will do this for the midpoint of each hazard interval. It will be done for each exposure scenario as well. Exposure is a fraction of a period of time for which a life loss estimate applies. Typically, we only consider day and night for exposure, but as discussed in Module 1, other scenarios can be considered as well and should be considered when they might impact the risk estimate. To calculate the average annual life loss, we're going to multiply the annual probability of failure by the exposure and incremental life loss, then sum the results to obtain the average annual life loss. After we calculate the average annual life loss, we will divide that value by the total annual probability of failure to calculate N bar, the average incremental life loss. N bar is the average number of fatalities that is expected should the dam or levee fail, considering all possible hazard and exposure scenarios. Continuing with the example that we've been working through, we will start with a breach life loss table shown on the left. Like we did for the system response, we are going to interpolate to find the breach life loss for the midpoint stage of each hazard range. We will do this for both the day and night exposure scenarios, and we will use linear interpolation. For the last interval, where we are considering exceedance, these are stages greater than elevation 911.8. It's not really the midpoint, but we will interpolate and use a breach life loss for elevation 911.8. Next, we will use the same procedure and interpolate to get the non-breach life loss at the midpoint of each hazard interval. The incremental life loss is the difference between the breach life loss and the non-breach life loss. For each exposure scenario of each hazard interval, subtract the non-breach life loss from the breach life loss to get the incremental life loss. For the second to last interval, elevation 901.3 to elevation 911.8, the math is shown. For the day exposure, the incremental life loss is equal to 495 minus 18, which equals 477, as shown in red. And for the night exposure, which is shown in green, it is 438 minus 21, which gives us 417. Now that we have the incremental life loss, the last thing we need to calculate the average annual life loss is the exposure. We are told to assume a 10-hour workday. So we will simply divide those 10 hours by 24, the number of hours in a day, to get the day exposure of 0.417. The night exposure will be the complement, 1 minus 0.417, which equals 0.583. For the night exposure, you could have also taken the 14 remaining hours and simply divided by 24, which also equals 0.583. Next, we multiply the day exposure by the day incremental life loss and add that to the product of the night exposure and the night incremental life loss to get the weighted incremental life loss. Finally, we sum the average annual life loss calculated for each interval and get a total average annual life loss of 1.29 times 10 to the minus 2 lives per year. Often, we will not report the exposure-weighted life loss and do the exposure weighting within the average annual life loss calculation, as shown by the equation at the bottom of the slide. Finally, we will take the average annual life loss that we just calculated and divide it by the annual probability of failure to get n bar, the average incremental life loss. The average annual life loss is 1.29 times 10 to the minus 2, and we'll divide that by the annual probability of failure, which is 5.07 times 10 to the minus 4. That gives us an n bar, which is equal to 25 lives per failure. This completes the marginal risk calculations for PFM1. We would then complete the same set of calculations for the remaining failure modes, PFM2A and PFM2B. The calculations for those failure modes are included in the companion spreadsheet. Similar to how we calculated the average annual life loss in n bar, we can calculate the average annual economic cost, AAEC, and the average incremental economic cost, $bar. The process and the equations are the same, but we do these calculations with dollars now instead of life loss. So far, the example covered up to this point has been for a single failure mode. What do we do when we have multiple failure modes? In Module 1, we discussed combining failure modes, and this is something that is worth reiterating so that we can be sure that we are combining the failure mode risk estimates in a way that is technically correct. We do not want to artificially inflate the risk by how we combine failure modes, and we need to be aware of the breach characteristics of each failure mode. There are several options available for combining risk. The joint risk model is the most accurate, but is also the most computationally intensive. For the common cause adjustment, intersection events are weighted and distributed by potential failure mode. In the competing risk model, it is assumed that the first failure precludes additional failures or additional consequences. And in the exclusive risk model, dependence among potential failure modes is assumed to be negligible with respect to both probability and consequences, such that the estimates can be summed. As discussed in Module 1, which model to use depends on the tools available and the accuracy required. Common cause adjustment has been the most frequently used risk model for dam safety risk assessments, but the Corps now recommends using joint risk or competing risk. Not discussed in Module 1 is what to do when the same failure mechanism is evaluated for multiple pathways. When multiple failure paths of the same mechanism in the same area are evaluated due to physical differences in geology, geometry, treatment, or whatever, we will combine the system response curves into a single composite curve by selecting the maximum probability of failure at each hazard interval if the expected breach characteristics and downstream consequences are the same. The composite system response relationship for the failure mechanism would then be combined with the project's other system response curves per the selected model. Here's a figure showing some examples of cross-sections where different flow paths would need to be evaluated for the same cross-section. You will want to consider flow passing above and below the core, above and below incline drains and filters, and above and below stability berms. To combine the risk estimates for different flow paths of a cross-section, we will take the maximum system response probabilities between the flow paths for a given hazard. Getting back to our example, we have 3 potential failure modes, and we will be using the competing risk model. PFM1 is concentrated leak erosion. PFM2A and PFM2B are both the same mechanism, backward erosion piping, and have the same consequences. So we will need to combine them into a single composite system response by taking the maximum at each hazard interval before adjusting the probabilities using the competing risk model. Here we have the marginal system response probabilities for the potential failure modes, and we are told to use the competing risk model. PFM2A and 2B are the same failure mechanism evaluated at different locations. So prior to performing the competing risk calculations, we must first identify the maximum probability between PFM2A and PFM2B at each hazard interval. As shown, the system response for PFM2A is highest for the first 7 intervals, and PFM2B is the highest for the remaining intervals. The maximum system response probabilities are carried forward as the combined system response for PFM2. Competing risk calculations were discussed in the Module 1 presentation. The results are shown in this table, and an example calculation is provided. Please refer to Module 1 if you need a refresher on competing risk. You will need to know how to do the competing risk calculations for homework 2. To then calculate the total project risk, we will need to complete the event tree math and sum the failure end nodes to calculate the total APF using the adjusted system response probabilities we just calculated. We will multiply the APF by n for each hazard interval or event tree branch at each failure mode and sum them all up to calculate the average annual life loss. We will divide the average annual life loss by the APF to get n bar. Lastly, we will do the same thing for the economic risk and multiply the APF by the dollar amount for each hazard interval or event tree branch of each failure mode, and then sum them up to calculate the average annual economic cost. For our simple example, after adjusting the system response of each failure mode using the competing risk model, the total project APF becomes a simple sum of the APFs calculated for each failure mode, APF1 plus APF2. The same goes for the average annual life loss and average annual economic cost. The non-breach part of the tree goes to 0 because there are no incremental consequences for the non-breach scenario. Having completed the incremental risk calculations, there are a variety of ways we can present the results. We've already discussed the little FN plot, the big FN and F dollar plots, and the individual risk plot. In addition to these plots, we can also create risk profile plots to show how the APF, average annual life loss, or average annual economic cost changes with an increase in hazard. Here is how the risk from our example plots on the little FN chart. Remember that the marginal risk for each PFM is plotted along with the total. The competing risk model adjustment is only used to compute the contribution to the total. The total plots more than an order of magnitude above the average annual life loss guideline, and risk reduction would very likely be recommended unless there are exceptional circumstances. The qualifier, unless there are exceptional circumstances, refers to a situation in which the government, acting on behalf of society, may determine that risks exceeding the tolerable risk limits may be tolerated based on special benefits that the dam brings to society at large. For risk profile or cumulative plots, we will calculate the cumulative APF starting with the lowest hazard interval and working up towards the highest peak stage. When we finish, the APF at the last stage should be equal to the total APF of the potential failure mode. The results are plotted stepwise. The plot makes it easy to see which hazard interval contributes most significantly to the overall APF of the potential failure mode. In this example, you can see how the steps get smaller and smaller as the stage increases, illustrating that these stages are contributing less and less to the overall total risk. About 90% of the risk here is coming from stages below elevation 880, and over 70% of the risk is coming from stages below elevation 870. Technically, this plot is supposed to be plotted in stepwise fashion, but that can be a bit of a hassle. If you have enough partitions, you can just plot the cumulative APF versus the midpoint of the hazard intervals. It will communicate essentially the same information, but it's much easier to create. We can create these plots for annual probability of failure, average annual life loss, and average annual economic cost. We can create them for individual failure modes, like on the previous slide, where we use the unadjusted system response. And we can create them for the total project risk, where we use the adjusted system response to get the potential failure mode's contribution to the total, as shown here. For each stage interval, we sum the probabilities from each failure mode to get the total for the stage. Then the cumulative is equal to the total APF from that interval, plus the sum of the APFs for all lower intervals. Once complete, it will look like this, with stepwise functions for the individual potential failure modes, shown in red, blue, and green, along with the total, shown in black. Next, here's how our example plots on the big FN plot. As you can see, the risk exceeds the guideline. Remember that this plot displays a probability distribution of incremental life loss. The probability of at least 10 or more fatalities is a little bit under 1 in 1,000, and the probability of at least 100 fatalities is just under 1 in 10,000. There are a handful of steps to make the big FN plot. To start, we are going to multiply the APF, calculated using the adjusted system response probability, by the exposure for each partition of each potential failure mode. The table to the right is a zoomed-in version of the table on the left, which was generated as part of the example we've been working through this entire module. Here, we see the portion of the table for PFM1. We have the APF for each interval. We multiply that by the day exposure in the top half of the table and by the night exposure in the bottom half of the table to get our probability F. Each of these scenarios has an associated incremental life loss. Remember the incremental N values we calculated earlier? Those are the same day and night values here that we will use to create what we will call our FN pairs, tying each probability to a life loss. We need all possible FN pairs across all exposures, partitions, and potential failure modes. Once I have all those pairs, I'm going to merge them into one big table and then sort them by the incremental life loss N. All the pairs from all potential failure modes and exposures are in this table. When we sort them, we want to sort them high to low. From these sorted FN pairs, we will calculate the big F, the cumulative probability, for each N by summing the little f's for that N and higher N's, much like we did when developing the cumulative risk profile plots earlier. For the first partition, the little f is going to be equal to the big F and is equal to 6.44 times 10 to the minus 8. I add 1.58 times 10 to the minus 6 and get 1.64 times 10 to the minus 6 for the next interval. I add 2.14 times 10 to the minus 7 to that and get 1.86 times 10 to the minus 6 for the next one. And I'll continue that process until I reach the very bottom of the table. When finished, the cumulative probability, the big F for the lowest N, should be equal to the annual probability of failure for the project. So to reiterate, merge the FN pairs in one big list, sort high to low by N, then sum the partitions as you move down the table to calculate the cumulative probability. The last step is to plot the data stepwise. The first cumulative probability is plotted with the first two N's. The second cumulative probability is plotted with the second and third N's, and so on and so forth. Once finished, extend the rightmost end of the curve straight down to the x-axis and the leftmost end over to the y-axis. The curve extends infinitely downward and represents the maximum incremental life loss. The curve is also extended to the left because there is no discrete point for n equals 0 because of the logarithmic scale. To calculate the individual risk, we simply multiply the likelihood of the most exposed person or group losing their life, as informed by LifeSim and our consequence specialists, by the annual probability of failure. In this example, we multiply 0.45 by 1.23 times 10 to the minus 3 to get an individual risk of 5.55 times 10 to the minus 4.